Hi students, welcome to videos on how to conduct experiments stage by stage. So in AEC lab, let us consider the DC power supply. So we know that it is AC to DC conversion. First and foremost thing is that. So let us do stage by stage. How do we conduct this experiment? So assume that you are connected, you have designed a 90, you designed a power supply which results in a 909 transformer. So now you are connecting the primary to 230 volt 50 hertz AC. This 909 actually corresponds to the RMS voltage of this transformer. Now first I have to ensure that whether this power supply is working fine and this transformer is working okay or not. To ensure that everything is fine, so let me first, before you proceed with any further connection, you measure what is the voltage that you're getting here. So use a digital multimeter and put it to AC mode and try to measure the voltage by connecting the red probe here, the black probe here, which are supposed to be positive negative here. So now this is, of course, for measuring AC, you can, even if you interchange that, only the sign will change, but it is better that you just connect it here, connect it plus here, sorry, red here, black here. You're going to get 18 volt as the RMS voltage that you want to measure. So this is 18 volt you're going to get. So maybe while doing the experiment, you may get 19, you may get 17, you may get 15 also. So these are the voltages what you're going to get. So this ensures that your transformer and the power supply is fine and you have done a proper connection. Let us proceed to the next stage where you're connecting a diode and a resistor to get the rectification. So let me say this is V1. So now I want to measure. So let me consider there's a 1 kilo ohm quarter watt resistor is connected. Quarter watt resistor is connected. So since you're connected a quarter watt resistor, so and so. So how much is the DC voltage expected here? Now again use the same multimeter. Use again, now it should be red and this should be black terminal here. So now this should be in DC mode. So in DC mode, how much voltage you're going to get? You're going to get V peak by pi. How much is V peak? V peak is 18 into root 2 by pi. So which are supposed to be around 25 by pi. So which is now almost 25 by pi happens to be around 8 volts. You're supposed to get 8 volts as the voltage that you're getting here. So now if you are getting 8 volts, you can proceed. Otherwise you have to check whether you have done this proper connection of this resistor back to this and so on. So once that is done, so now this is what is expected. You are getting close to 8, 8.5 or 7.8, anything is fine. So this should be in DC mode. Very important that this is a AC voltage, this is a DC voltage. Next comes the filtering. So till here we are using a digital multimeter to verify all those things, so it's fine. So now let me connect a capacitor. So again, as per your design, assume that your design happens to be 500 microfarad. So now when you connect a 500 microfarad, of course now the DMM will stop here. So you're not supposed to use DMM anymore here. Now you have to use the unlock discovery kit. Connect one of the channel to this, maybe channel 2 plus can be connected here, and you can see the waveform will be something like this. So you'll be having charging, discharging, charging, discharging. So this will be keep happening. So how much is the voltage that you're expecting? You're expecting a voltage which is almost how much will be the voltage? This peak voltage will be the peak voltage will be almost around how much? It will be almost 25 volts. So this is almost 25 volt is the peak voltage. And how much is the ripple you are talking about? So this you should get almost, because this is your input waveform what you are applying, and that will be rectified. And okay, this is what you'll be getting, a rectified one, bit slightly lesser by 0.7 volts. This is what you're getting, and ultimately you're going to get this as your charging, discharging. So what is this voltage? This is almost 25. So this is 25, and this voltage is, depending on your design, this will be 1 volt to 2 volts also. How do you measure this and this? So this 25 volt can be measured using the C2 max in your AD kit measurement. And how do you measure this peak to peak? This is using C2 peak to peak. So using these options, you can able to ensure that you are measuring the peak voltage and then peak to peak of this using the measure option in AD kit. So once you are done with this, okay, this will take hardly 10-15 minutes to do all these connections. And be very careful. This capacitor is having a polarity plus minus. So you have to identify the capacitor will be on one side, it will be a strip, so that will be usually negative. Connect that here. This is plus. This is an electrolytic capacitor and stores the DC voltage. By mistake, if you are connecting this minus and this plus, after some time this will burst. So this will burst, and of course that's not a good sign for a student to do a wrong connection, something like minus to a positive voltage, a larger voltage, and plus to a lower voltage. So that's why, so you have to be very careful here. Of course, I can represent this as a ground in my circuit. So once you're done with this, you are having a proper filtered DC voltage, so that can be given to the regulator. Now you connect the regulator, whatever is the regulator. Supposing that if it is 7805, identify which is input terminal. No, it should be very clearly identified. Suppose if you have a 7805 regulator, so usually this is 7805. Look for the data sheet, identify the terminals. So one is the input, 2 is usually the ground, and 3 is the output. For whatever case, you will be allowed to take the data sheet inside the examination hall, or whenever you are doing any experiment, you have to keep the data sheet with you. Identify input, ground, output. So connect terminal 1, terminal 2, and terminal 3 as your output point. So now if you measure at pin number 3, since you have applied sufficient voltage, at pin number 3 you will be getting exactly 5 volt. Exactly 5 volt. So this is how so easily you can able to do it. So once you're getting 5 volt, now even if you remove this resistor, so there's no harm. Now you can remove this resistor, this will be still 5 volts. So I'm again repeating. To start with, you started with this resistor, then you put a capacitor, then you put a regulator. But after getting this 5 volt, even if you remove this capacitor, this will be still at 5 volt. Suppose if I remove this resistor, if I remove this capacitor also, if I remove this capacitor, what are the type of waveform that will be applying to the input of the regulator? This is the type of input that will be applying to the input of the regulator. So assume that this is 25 volt and this is also 25 volt, this is 0 volt. Now this is the input to the regulator. So when this becomes the input to the regulator, when you remove this and this, what is the output of the regulator? Output of the regulator almost follows this till around 6 to 7 volt, and then it becomes constant at 5 and again comes down. This is what is that you're getting. So this will be constant at 5 volt. This is constant at 5 volt. So this is what is expected when you remove both R and C from the circuit. This is for line regulation. This is for line regulation. So when you are getting this as your output waveform, you have the input also fed to channel 1. So input also fed to channel 1. If you put it to XY mode, you will get a characteristic something like this. So this is your input voltage, this is output voltage. This is around 6 or 7 volt, you will get a constant voltage of 5 volt. So this is what add XY in your measure will going to result in. So this is what is known as line regulation. So till the input voltage crosses around 6 or 7 or 7.5, the output voltage is not constant 5 volts. If the input voltage is beyond that minimum voltage, what we discussed in one of the video from the data sheet, if it is more than 7.5, you'll go to get constant 5 volts. So that's what is line regulation. To do the load regulation, what you can do is Again, put the capacitor back. You're using the capacitor, of course. You can put the capacitor back. So now you have this constant 5 volt. Now you use the resistor of very large value. Use a DRB of, okay, maximum value. So when I say maximum, you make all resistors maximum, then you start reducing. So when I say maximum, don't, there is no point in keeping 100k also maximum, okay, 10k is also maximum. Keep at least hundreds of ohms. So I'll just repeat. To do the load regulation, what you have to do is, so let me write the circuit again. Let me write the circuit again. So you have this, you have this, you have the regulator, and then you have this DRC. Now keep this at around 100 ohm. So when you're, maybe keep it at 1k, that is 100 into 10 and then 10 into 10. So you have these knobs of 100 ohm and then knobs of 10 ohm. So you keep them in 10, keep them in 10. So that will result in almost 1.1 kilo ohm. So make all others as 0, 0, 0. So because you're going to have 1k, 10k, 100k, so on so. So all those things you make it 0. Keep the last two, or if you have a 1 ohm resistor also, keep this also 10. So now you have all these three in smaller values of knobs, so as 1 ohm, 10 ohm and 100 ohm. You keep them in maximum, maximum, maximum. So you almost have 1.11k. Now you start reducing. Now you now you keep observing the voltage here. The voltage will be 5 volt when it is all the three are 10 10 10. That is in the position 10. You make start reducing this. So when you start reducing this, this will be fairly constant. This will be fairly constant. You make this 0. So you make now this 100 ohm knob to 0. So this 10 ohm knob is still at 10, and 10 matlab, okay, 10th position, and 1 ohm knob is also at 10th position. So at this point you will be still having 5 volts. Now you start reducing this. So make this 0 and then start reducing this also. And maybe when you're coming to a stage where it is like, okay, 8, maybe 8 ohm, 6 ohm, 7 ohm, then the voltage starts reducing. So you just note what is V0 and what is RL for different values. So for different RL, what is V0. So that will give you the load regulation. So once you know RL, you can find what is IL, which is nothing but V0 by RL. So this is IL versus V0. So what is this IL? So you'll be knowing what is V0. You'll be knowing what is the resistance that is kept here. And for every resistance, keep noting the output voltage. Then you can plot a graph of load regulation. This is for load regulation. So this is how comfortably we can able to do getting the power supply a constant DC voltage and doing the line regulation, load regulation. Then let us move on to how to do AC amplifier. To do AC amplifier, of course, it's very simple. Properly connect the transistor, identify the emitter, collector, base. Please ground the emitter first. Use a resistor of maybe, of course, whatever the design that you are using. Maybe if it is 47k, connect it to VCC. Connect a 2.2k resistor to, from collector to VCC. Again, you use a DRB between the base and the ground. So this is R2 DRB, and you have this coupling capacitor, and you have your source, which is in the form of first channel of your wavegen, and this is your C2 plus, and you are observing C1 plus input. So once you made this, of course, doing connection is very important. So I have to connect the circuits very perfectly and make sure that none of the components are touching unnecessarily other than the expected connection. So now without applying any voltage, please don't apply the voltage. Apply only VCC and ground. keep the value of R2 to the design value, which is around 5K or 6K or whatever the design what you kept, and see what is this voltage. So voltage, the DC voltage, using the scope of your AD kit, measure what is the voltage here. So voltage here should be, assume that I'm just there in the AD kit. This is the, okay, this is 0, this is -5, this is +5. This is your scope screen. Suppose if your signal is here, suppose if your voltage is here, if the DC voltage that is kept here is here, means, so now what does this actually indicate? This is indicating what is the voltage at collector, which is nothing but VCC minus IC into RC. So now if this is equal to 5 and this is the supply voltage which is 5 here, so if this voltage is 5 means, so then the drop is almost 0. When the drop is almost 0 means, so you don't have sufficient base current, so that's why there is no IC, that's why there is no drop. So what you have to do now, you have to increase the value of R2 using DRB, so that this current increases, so that this value is not 0. This is something like 1 volt to 2 volts also. When it is 1 volt to 2 volt or 2.5 volts, this voltage starts coming down, so it just comes down to this, and it will come to the expected value, which is 2.5 or whatever as per your design. This is a must thing before you apply the wavegen. I'm just repeating, you have to ensure that R2 is sufficient that you'll get 2.5. So other case may also happen. Assume that you have done the connection, this is 0, this is 5, this is -5, this is again the scope of your AD kit. Assume that you have kept some value of R2 unknowingly, and if the voltage at the collector is at this point, assume that it's almost at 0 volt. What does this mean? What does this mean is, so whatever this voltage is, this voltage, that is V5 minus something. So 5 minus 5 is 0. What does this 5 minus 5 actually stands for? So you have a very huge current flowing, so that the entire voltage which is there here is being dropped here. So you are left out with nothing. So what to do now? I have to reduce the value of IC. So let us not change the value of RC. Let me change IC value. How do you change IC value? IC can be reduced by reducing R2. Now you reduce R2 so that this voltage rises to 2.5. There are two possibilities. The voltage can be at 5, the voltage can be at almost 0. If it is at 5 volt, you have to increase the value of R2 so that it comes down. If it is almost at 0, then you have to reduce the value of R2 so that this goes up. So this is the only key thing that you have to remember in CE amplifier. This is very important. Keep this whatever the value, and this has to be kept very correctly. Suppose by mistake if you keep 10k or 100k as the resistance in the DRB, then you'll get this one. If you keep in terms of 1k or 2k, you'll be having this condition. So make sure that if you are there either in this condition or this condition, you should know why it is so. If you are in this condition means no sufficient current is flowing, you have to increase R2. If you are there in this condition is heavy current is flowing, you have to reduce the current, so that you have to reduce the value of R2. So this IC has to be reduced, so that can be done using reduction of R2. Okay, once this is done, of course, for doing all these things, so I just said that it is 0 plus 5 minus 5. To get this, your volts per division should be 1 volt per division, that in the scope of your channel. So channel 2 should be in 1 volt per division, Y scale. Horizontal, you can just keep whatever the thing, that depending on your frequency of the signal. If this is done, then you can come to this wavegen, and in that wavegen channel 1, select the frequency as a 20k, 50k, 100k. You can choose whatever frequency that you want. Keep the amplitude around 0.01 volt, very small voltage, 10 millivolt, and then offset should be 0. Offset is 0, and then you what else you have? I think that's it. Okay, symmetry should be 50%, all those things. So make sure that the frequency and amplitude and offsets are set as per this. The moment you apply this, turn on your wavegen, and you'll get a waveform which is exactly this. This is your output. The input would be out of phase with this. So once you are through with this, next you know what to do. You know channel 2 peak to peak, channel 2 average, and the channel 1 peak to peak. So this peak to peak by this peak to peak will give you AV. This average will give you the collector voltage, and using the collector voltage you can find what is IC, which is nothing but VCC minus how do you find this? Using this VC value, what you can do is VCC minus VC by RC will give you a IC, the collector current. So once you know the collector current, which can be used to find the theoretical gain expression or gain values, all those things, because GM is nothing but IC by VT. So you can use this value of IC. You know VT as 26 milliwatt. You can find what is the AV of the circuit, which is GM into RC, because you'll be knowing what is the value of RC that you're connected. So using this, you can easily comfortably measure what is the gain of the amplifier that you're getting. So once you're done with this, suppose now while okay, this is if you're keeping at 0.01 related, assume that you keep it at 0.01, and if you're not getting the waveform, so please check whether this coupling capacitor is properly connected or not. So this has to be properly coupled here, and then hardly when you're getting this almost close to 2.5. So if you've made the proper connection and if your wavegen is properly applied, so this will certainly come. Next is the frequency response. For frequency response, you use the network. So there you select what the start frequency, because you are looking for a frequency response something like this. You're looking for a frequency response something like this. This is your magnitude plot. This is frequency. This is gain in dBs. You'll keep it. So you start from 50 hertz. You can stop frequency can be 10 megahertz, and you can have 100 points per decade, and the input should be again 0.01 volt, and of course you can take the magnitude as around 50 dB as a magnitude, and the range can be around 100 dB or maybe 60 dB, 80 dB, whatever. So you'll get comfortable with this. Then place one cursor here, place the other cursor here, so that the difference is 3 dB. 3 dB actually corresponds to 3 dB always corresponds to half power point of power point. So half power meaning if the power is P1 here, the power should be P1 by 2. The corresponding to this P1, if there is a voltage of V1 at half power point, I'm going to have a voltage which is V1 by root 2. So how do you get this 3 dB is, so now I know what is 1 over root 2. 1 over root 2 is 0.707. If you do the log of this, 20 log of 0.707 happens to be minus 3 dB. So you're getting that minus 3 dB, that is difference from here to here is 3 dB, which is lower value. That's why we call it as a 3 dB bandwidth. So any frequencies before this, then the power is less than half of the maximum power. So that's why we won't consider these frequencies. Frequencies from FC1 from this side, and on the other side you can have another FC, which is FC2. Again also you're looking for V1 by root 2 or P1 by 2. P1. This is your power, this is your voltage. So that's why now it's again 3 dB down from this. So you just look for half power bandwidth here. So then the bandwidth happens to be FC2 almost, because this FC1 is, it's actually FC2 minus FC1, because FC2 is far greater than FC1. We write bandwidth is equal to FC2. This is in terms of megahertz, this is in terms of hertz, so that this is negligible, so that you will have this as your bandwidth. And of course this is your gain, and this is your 3 dB gain. And of course you can also find what is the phase shift. So you'll also have one more graph, okay, one more parameter, which is the phase. So phase will be 180 degree here. Phase will be 180 degree. So what extra thing that you can do is change the resistance RC, then this gain will increase or will actually reduce here like this. So then bandwidth will also change. So that's what is the next process of finding what is gain and bandwidth for different values of RC. Do it for 1K, do it for 2.2K, do it for 3.3K. Whenever you're doing this, don't adjust R2 again. Don't adjust this R2 again and again to make it at 2.5. So when you're changing this to 1K, 2.2K, 3.3K, keep R2 as it was there in the earlier case. So your gain will change and then do the gain bandwidth measurement. Hope okay, this will give you a clear idea of okay what you're going to, what you're supposed to do for CE amplifier. Coming to CC amplifier, which goes this way. Again, doing the proper connection on the breadboard is the key for any circuit for that matter. This is your input voltage. So this is whatever the value that you have calculated, you connect that R1. R2 you have a DRB, this is your RE. Maybe you can choose whatever value that you have. So let me not talk about the value. So this is your V in, this is V0. Again, without applying the input voltage, make sure that the voltage here becomes close to 2.5 volts. Close to 2.5. If it is not, supposing that this is your scope, this is at 0. Supposing that you are getting at 0 here. Suppose if the voltage here is 0, meaning that so IC or the current that is flowing is very less. So what I have to do, if it is here means you have to increase the value of R2 so that IC will increase, so that this drop will increase, so that it will come, it will go up. So now if you want to increase IC, you have to increase R2 now. So this is what you're doing. Assume that it was already there here. It was already there here, very large. So then I have to bring this down. How do I bring this down? I have to bring this down by reducing the value of IC. That can be done by reducing the value of R2. If it is already at the top, you have to reduce the value of IC, so that because this is your voltage, so this is VE. So VE is equal to IC into RE. If this is very large means I have to reduce this. If this is very large means I have to reduce this. How do you reduce? Change R2. Because if you are changing R2, the VB will reduce. If VB reduces, naturally IC will reduce. So that's the whole idea of I have to reduce the value of R2 if it is already at 5 volt. This is at 5, this is at -5. So once the DC conditions are fine, if you are having the output voltage, the DC voltage here, then you switch on this signal, AC signal over here as W1, and you can certainly apply an amplitude of even up to 1 volt, because this has got a gain of very less gain, which is less than 1. Even if you apply 1 volt sine wave here, 1 volt sine wave, the output voltage will also be of course it will be in phase. So certainly it will be in phase. So I just write okay, it is in phase with your output signal. It's not a harm. Even you can apply input of, so this is the input amplitude 1 volt. The frequency can be again 50 kilohertz, 20 kilohertz, or it can be 100 kilohertz also. So it should be in terms of hundreds of kilohertz or tens of kilohertz. So once you are done with that, of course you can do the frequency response as in the earlier case, but since the gain is less than 1, so there is no point in frequency response for this. May not be very relevant. Only thing is that do the connections properly, measure the voltage at this point, which should be half of VCC. If it is less, increase R2. If it is already more, reduce R2. So that's the stuff. So this is about CC amplifier. Then comes which circuit? Let me just take. Then comes your op amp, inverting amplifier, non-inverting amplifier. So this is op amp applications, maybe op amp amplifier. For op amp amplifier, make sure that your op amp is working fine. So for that, make sure that you are connecting plus VCC and minus VCC to appropriate pins. Let me ground one of them. Let me apply 1 volt. The moment when I do this, so I should be getting plus 5 volt. I should be getting plus 5 volt because V plus is more than V minus. Suppose if I apply minus 1 volt here, if I apply minus 1 volt here, of course, when I say plus VCC, need not be plus 5 volt. Whatever voltage that you get, that will be called as plus VSAT. It can be plus 3.8, it can be plus 4.2 volt, it can be plus 3.5 volt. No, this is your plus VSAT. The moment when I apply negative voltage, the voltage that I'll get here is minus VSAT. Please note down that plus VSAT minus VSAT, which is very essential before you start rigging up the circuit as per your expectation. So once you are through with plus VSAT minus VSAT, it will ensure that your IC is working fine. IC is working fine. Then you go for the exact circuit. If it's an inverting amplifier, do the connection minus plus, ground it here. Use one resistor of fixed value, the one can be a variable one. You can use this as a variable, use it as a fixed one, maybe 10 kilo ohms, and use your wavegen, maybe W1, which happens to be input. Look at what is V0. Use second channel positive for measuring output. Use channel 1 for measuring input. Again, now the important thing is that these op amps will have a cutoff, a lower bandwidth. So don't keep frequency of this input signal too much. So let us keep the frequency in terms of maybe 100 hertz, 100 hertz. So this is not kilohertz, this is 100 hertz. Maybe you can keep at 500 hertz. So this is the frequency what we are talking about when you're doing a op amp related experiment. Please don't apply high frequency signal. This should be a low frequency signal. And you can apply, of course, depending on what is the gain and all those things, even you can apply 0.1 volt, 100 millivolt as your input voltage. Look for what is the output voltage. Of course, because in this case the input is 0.1 volt, and depending on the gain, output will be inverted and you'll get an amplified version. Of course, that amplification can be more than one or it can be less than one also. It's out of phase. Again, what you have to measure now? You have to measure V0 peak to peak by V in peak to peak. So that will give you the gain of the circuit. That's what you are doing in time response. And in frequency response, you again plot the frequency response. You start from 50 hertz to maybe 200 or 500 kilohertz. No need to go up to 1 megahertz, and 10 megahertz is not required as you did in case of C amplifier. The end frequency need not be, or the stop frequency need not be in terms of megahertz. It can be in terms of hundreds of kilohertz. So now you can keep the cursor here to know what is the DC gain. So this we call it as DC gain, because why it is called as DC gain is because you are measuring at a low frequency. Since it is measured at low frequency, it is called as DC gain. So this is frequency, this is gain in dBs will be there. So depending on whatever is the gain of this, and you're going to get 20 log of that gain as the value that is here. Then you keep one more cursor at 3 dB down. This is from here 3 dB down, which happens to be the bandwidth FC1 or only just FC. So there are no two cutoff frequencies. You have a cutoff frequency only here. This is starting flat. Change the value of RF, do the measurement of your gain V0 peak to peak by V in peak to peak, and then measure what is this bandwidth. So maybe of course you can keep the amplitude as maybe 0.1 volts also at the input, because here also you are supposed to keep the amplitude in case of while measuring the frequency response that is in network. Keep the amplitude as 0.1 volt. You will comfortably measure this gain. Suppose if the If the gain is too much, then you have to keep 0.01 volt so that output is not distorted, so that you get a proper waveform. So you tabulate the readings as per the expected things, and then so of course same thing is applicable for even the inverting amplifier, non-inverting amplifier. The circuits will change, and that's it. Then comes square wave generator. Square wave generator, you start with again checking the op amp, making out plus V side minus V side. So you have this circuit, so connect some resistors of any value that is designed, and you are just grounding it here. You have a capacitor here, and then you can connect a DRB here. You can connect a DRB here. This is grounded. This is CT, RT, and this is, of course, you'll measure plus V side and minus V side. Whatever the values of R1, R2 that you're connected as per your design. So now as soon as you make this connection, there is no doubt that you'll not get the output. So you will certainly get the output if the connections are properly done. So plus V should be connected to 7, the minus V should be connected to 4, 6 is connected to output, 2 is your inverting terminal, pin number 3 is output, the non-inverting terminal. Connect these things, you will certainly get a waveform which is going like this. This will be a 50% duty cycle. So your capacitor voltage at this point will be going like this. So it will go up to beta V sat minus beta V sat. So what is that plus beta? The voltage here will be plus V sat R2 by R1 plus R2. The voltage here will be minus V sat R2 by R1 plus R2. So those are the voltages up to which your capacitor will charge up to. So if the capacitor voltage tries to go above this, then output makes a transition from plus V sat to minus V sat, minus V sat. So whatever the voltage that you measured before this, it will be going there and coming here. To have different duty cycle, you'll connect circuits like this. Of course, you can put, maybe you can use only one DRB here. So this is 2 diodes, D1, D2. So maybe you can make this 10K. Can make this 10K, 10K. Duty cycle is 50%. Make it 100K. This is 10K. Then it is less than 50%. Make this 1K. Make that 10K. It is more than 50%. So you can play with the values of R1. This RT and this RT2. So depending on your design, you may have to choose that value. So there should not be any difficulty in getting the output for this particular circuit. Maybe we can use this as 0.1 microfarad. Use this as 10K, 10K. That's it with that square wave generator. This is square wave generator. Again, how do you measure this? Again, 1 volt per division should be your scope positions, and no offset for both of them, so that you can see what is this in C1. This is your plus minus C1 plus, and this is C2 plus. So this happens to be the second channel. You'll get this. Of course, I have written blue color as C1. Actually, blue color is C2, and or yellow color is yellow color will be C1 in my AD kit. So this is about square wave generator. Then comes what? This Schmitt trigger. Schmitt trigger. So in this Schmitt trigger, we have the circuit, one of the simplest circuit. You can use this. This is R1, this is R2, and this is your this is input. Usually you will be using W1, and here you'll be using W2 as V reference. Again, to start with, you have to measure plus or minus V sat, whatever is the voltages. Set the values of R1, R2, and V reference as per your requirement. Keep the input voltage amplitude greater than VTH, and VTL, whichever is the maximum. So whichever is the maximum value, you have to keep the input voltage more than that. So you keep input as 5 volt amplitude, which is the maximum possible here. And we know that as soon as the suppose this is VTH, if this is VTL, as the input voltage crosses VTH, so I should be very particular about this waveform. So we should be clearly knowing what happens when. So this is whenever your input voltage increases above VTH, output goes down to minus Vsat. Whenever your input voltage goes below VTL, output goes to plus Vsat. So this is what's happening here. This is plus Vsat and this is minus Vsat. To measure VTH VTL, this is actually a VTH point and this is your VTL point. To measure this VTH VTL point, you can actually use this as C1 plus. When you are using this as C1 plus, whatever waveform that you get here, this corresponds to VTH, this corresponds to VTL. If you are measuring the waveform at V plus, that is pin number 3 of your op amp, 7 for 1. So if this is 7 for 1, then this is 3, this is 2. If you are using channel 1 to measure this, so then VTH is this, VTL is this. So use the X cursor to find out what is this voltage, and tally that with your expected theoretical value. So this is about Schmitt trigger. So, and of course you can also do the add xy. If you do add xy, then it comes out to be this. So how it comes, depending on what is VTH VTL, you'll get it as this. This is your this is your V0, this is your Vn. This is plus Vsat, minus Vsat, so, and this is your VTH VTLs. Again, more importantly, I talked about the amplitude. The frequency has to be very less, maybe 100 Hertz. If you keep larger frequency, then you'll end up with this type of thing. So this will keep going like this. So this will take some time due to slew rate. If the frequency is more, then you'll end up with this type of waveform, which you should avoid. So let us keep the frequency as low, maybe in terms of like hundreds of hertz, 100 hertz, 500 hertz is fine. Don't go for 10k, 5k, 100k. Don't go for such high frequencies. So go for frequencies in terms of hundreds of hertz. What else you have? There is the 555 timer. Okay, 555 timer is again a straightforward one. So to check the 555 timer, the best thing you can think of doing is, this is 555, this is VCC, this is a reset, pin number 8, pin number 4, this is pin number 1 is ground. You connect these 3 terminals. The moment you connect these 3 terminals, at pin number 5, which is the control voltage, you will get 2/3 of VCC. So you'll be getting almost 3.33 volt at pin number 5. If you connect this to VCC, pin number 8 and 4 to VCC and 1 to ground. So this, if you are measuring the voltage at pin number 5, the voltage is 3.33. So that ensures that 555 timer is okay. Then you do rest of the connection. To make this voltage constant, you connect 0.1 here, then carefully connect one resistor between this and 7. Let me name it as R1. Let me connect one more resistor between this is 8 and 7. Between 7 and 6, you connect one more resistor, short 6 and 2, and connect a capacitor to ground from 2. This is my timing capacitor. This is my circuit. So using this circuit, decide depending on what is the value of R1, R2, you will get the frequency of certain duty cycle. The duty cycle is always more than 50%. Duty cycle is always more than 50%. If you want to get a duty cycle less than 50%, then I have to use a diode. This is for any duty cycle. You can get a duty cycle less than 50% or more than 50%, then If you use a diode, so this is meant for any duty cycle for that matter. Suppose if you are getting the waveform at pin number 2 as something like this, and at the timing capacitor, the voltage will be going from VTL to VTH, again to VTL. It will be going like this. This is VCC, this is VTL, this is VTH. This is your on time, this is your off time, total time, duty cycle, all those stuff. And if I don't use this, it will be 3.33. So there is a possibility that I can use this one of my term. Of course, there is no input applied to any of the circuit. That's why it is called as free running oscillator. Free running oscillator, which is nothing but a stable multivibrator. A stable multivibrator. This astable multivibrator can work like a voltage controlled oscillator if I connect W1 here. If I connect W1 here, and if I vary the DC voltage from 1 volt to 2 volt, 2 volt to 3 volt, 3 volt to 4 volt, 4 volt to 4.5 volt, or maybe 3.8 volt, or maybe 2.5 volt. So then my whatever this voltage that I'm applying here, that becomes VTH. That becomes VTH. And what is VTL? VTL is always half of VTH. Half of VTH. If I change this VTH, then VTL also changes. Then T on will change, because T on is given by maybe depending on what is for this particular circuit, it will become R1 CT ln of V SAT or VCC minus VTL by VCC minus VTH. So as my VTL VTH changes due to the change in this VTH, so naturally your on time will change. If your on time changes, then your total time will change, the frequency will reduce. Of course, T off remains the same. T off remains the same for whatever the value of VTH VTL. So duty cycle will change, frequency will change as you change your VTH, which is nothing but the control voltage. Control voltage. So that's why this is called as VCO, voltage controlled oscillator. Because when you're changing the control voltage, you are changing frequency. So is your old frequency of your oscillator controlled by the voltage? So this is how it is related. So this is your control voltage is change the frequency. That's why it is called as VCO. So this is a stable multivibrator using 555 timer. Of course, you have to make this voltage at 1 volt per division. This will be almost 5 volts, or maybe 3.8, 4.2, 4.3 volts, or whatever the voltage that you're getting. Next comes the what is that? Monostable multivibrator. Monostable multivibrator. Again, check your 555 timer by connecting pin number 8 and 4 to VCC. Okay, ground this pin number 1. You can use a capacitor for 0.1 microfarad to stabilizing the voltage at control voltage. This is 555, and this is pin number 2. Use one of the channel, maybe channel 1 to give the trigger signal, and you're using a desired value of RT/CT here. This will go to 7 as well as 6. 7 is discharge, 6 is threshold. This is RT/CT. So you have to be very careful with this control voltage, the trigger signal. So trigger signal should be something like this. So you should apply. So this is 5 volt, this is 0 volt. How do you get this 0 and 5? The amplitude should be 2.5, offset should be 2.5. So let us have the frequency as 100 Hertz. Let us take the duty cycle as maybe 95%. So I'm applying a trigger signal whose amplitude is between 0 to 5 volt with a 95% duty cycle. That means your off time is very, very small. Make sure that the trigger signal is valid only when if it goes below VTL. If it goes below VTL, then it is perfectly fine. So so let us see how does your output will come. So now we will suppose for this input signal, my output, suppose this is my output. So output goes to quasi-stable state upon getting a trigger signal. Let me just see. Now this is your output voltage. This is stable state. This is quasi-stable state, temporary stable state, which is 5 volt here, and this is your T pulse width. Your capacitor will be charging from 0 to VTH. 0 to this is VTH. So this is how it comes. Very importantly, you have to keep this voltage between 5 and 0, that is achieved using 2.5 and 2.5 as your amplitude and offset. There is another way of giving this type of signal for larger this one. So I can generate this using either wavegen, or I can use a push button like option to generate it. Maybe I can at pin number 3 I can have a LED. I can have a LED so that it glows whenever the output is high. So let me connect 1K. I have a switch here. When I don't push the switch, the voltage here is 5. So V trigger is 5 volt when I don't push it. So output voltage is 0. So output voltage is 0 here. Output voltage is 0. The moment I push it, the voltage goes down to 0. Moment I release, this goes back to VCC. The moment when I just pushed it, this goes to quasi-stable state, remains in quasi-stable state for a time period decided by RTCT, and then again comes down. Whenever it is coming down, make sure that this switch is not closed. When the switch is not closed means it is VCC. So this will be coming down after the TPW. If you again press it at some point, as soon as you press it, the output goes to high state, remains there as high for a predefined time, and again comes down. There is one more way of checking this. Suppose if I'm applying, suppose what is required here is, assume that your 2 millisecond. Assume that this is 2 millisecond. I have to keep this time period always greater than 2 millisecond. Let me take this is 8 millisecond. This is 8 millisecond, and this is hardly 0.4 millisecond. So to get a 2 millisecond pulse width, I have to have the off time should be 0.8 millisecond. Of course, the duty cycle is not 95%. I'm just simply giving some values. This is 0.8, this is 0.4 millisecond, this is 8 millisecond. With this, I'll get it properly. Suppose assume that I want to have 2 millisecond, but my trigger signal is hardly, assume that I'm applying a trigger signal very repeatedly. Assume that I'm applying the trigger signal repeatedly. Suppose this is my trigger signal. In such case, what happens? The output voltage goes high here. Suppose if your output, the pulse width is from here to here. Assume that this is my pulse width. This is my pulse width. So what happens to the output is, this will be considered as a valid trigger signal. Output goes high. These trigger signal, because now the output is high. Output comes down to 0 here, because this is my valid pulse width. So within this valid pulse width, I have one signal here, one more signal here. So these two trigger signals will not be considered at all, because the output voltage is still in quasi-stable state. A trigger signal is considered as a valid one only when the output is in stable state. So this is a trigger signal coming. What is the state of your output? It's in quasi-stable state. So what is the state? It's in quasi-stable state. Now the output has gone to stable state here, or the mono shot has gone to stable state. So now I'm applying a trigger signal here. So when I'm applying a trigger signal, the mono shot is in stable state. Now it goes to quasi-stable state, remains in the temporary state. So this is my TPW. What does it mean is that if you are applying a trigger signal before the end of pulse width, it will not be considered. These are called as uh, non-retriggerable. You cannot re-trigger within the pulse width by applying a trigger signals. So these are called as non-retriggerable monostable multivariate. Monoshot we call it as. So this 555 timer is a non-retriggerable monoshot. Non-retriggerable monoshot. Okay, remaining few experiments we'll discuss it in next video. Thank you.